All right, so the chi-square practice problems that you got today, you'll notice it says it's 1,600 cards. That's the total number of cards. And then it asks you for the four categories: spades, hearts, diamonds, and clubs. And you'd expect that in each of these you'd have about 1/4, right? 1/4 of the 1,600 is going to be spades, 1/4 is going to be hearts, 1/4 diamonds, 1/4 clubs. So if you look here at the answer set that I'm putting out for you, you'll notice that 1,600 is divided into 400 each of spades, hearts, diamonds, and clubs. Now, a lot of you get negative numbers, although I don't understand how you're getting negative numbers. If you're squaring the difference, it's always going to be positive. So if you get a negative number, you did something wrong, and the magnitude of the number is not going to change, because if you subtract 4 from 2, you get 2. If you subtract 2 from 4, you get 2. It's -2, but it's still 2. If you square it, that -2 becomes 4, right? So it doesn't really matter if you're squaring it, that you have a negative number inside the parentheses. All right, so you got 1/4 each of these. That's your percentage. That's what you'd expect. Your percentage, of course, would be 25%. So 25% spades, 25 hearts, 25% diamonds, and 25% clubs. But you don't need the percent to calculate chi-square. You need how many. You need the number. So you have to take that 25% and multiply it times 1,600, and that gets you the number 400. So that each of the suits would end up being 400 each. Now, in this answer set, they calculated the Z stat. You don't need to know the Z number. The Z number is a different. It's a different way of calculating chi-square. We use chi-square, as I said, and I think in a simpler format, and I think I really don't want to get into calculating the Z number. What I'd like you to do when you're doing your problem is the following, right? Which I showed you in class, which everybody should be able to do at this point. So you should take your observed number, and you should subtract your expected number, right? Or theoretical. You should square that, so that should be inside parentheses. You should square it, then divide by the expected value, and that's going to give you some magnitude, some number, no units, and that's going to give you a magnitude each time. You're going to sum up those numbers. You're going to sum them up. So that for each one of the categories. So you do that. You do this for the hearts. You do this for diamonds. You do this for clubs. You do this for spades, and you end up with a chi-square number. Now that chi-square number, as it turns out, if you sum up the square of the Z numbers, it turns out to be the same thing. But let's not worry about Z numbers. They did in this sample set, they did calculate Z, but don't worry about it. So your critical value is again found in the chart, and when you have four categories, how many degrees of freedom do you have? I hope you said 3. So remember, the degrees of freedom is n minus 1. So your degrees of freedom here is 3, and if remember, we're always looking at 0.05 or 5%. That's the average. Now, if the problem tells you some other number, you just find that particular percentage of accuracy that you're looking for. So 0.05 at 3 degrees of freedom, our critical value is 7.815, and here it is in 7.815 in the answer set. So 2.48 is smaller than 7.815, so you accept the hypothesis. And what hypothesis are you accepting? It says, in a test, you observe the following: could it be that the suits are equally likely, or are these discrepancies too much to be random? So is this discrepancy too much to be random? So you're looking at the expected. You'd expect to see 400 if they weren't. If you'd expect them to be 400 each. If it is in fact equally likely, and you obviously they're not coming out 400 each. They're coming out slightly different, and the question is, are these observed numbers too much to be random? And the answer is no, right? So we're saying that this falls within the randomness because the chi-square, within the accepted randomness, because the chi-square is smaller than that critical value from this chart. And that's it. That's the chi-square for the first problem. All right, so this is the same problem, except this time where before you just had to worry about spades, hearts, diamonds, and clubs, which would have been 25% chance each. Now you have to include the jokers in your calculations. So there you have a fifth category you have to worry about. So as you do your chi-square for these 5 categories, now you look at the expected results. Let's take a look at the answers. So you'd expect there to be about 24.07% chance for each of the suits, spades, hearts, diamonds, and clubs. You'd expect about a 3.7% chance for jokers. Now your total number of cards is 1,662 because it's Vegas, so they give you more than one deck. So when you look at it, you end up with a different set of counts that you did in the previous problem. So instead of 400, you have a 400.1, 400.1, etc., and 61.6 at the end is what you would expect for the number of jokers. So that's the count. So that's what you would use in your calculations. Now again, in this problem set, they use the z number to calculate chi-square. You know from the previous problem and from your notes that all you have to do is take your observed minus your observed minus your theoretical, square it, divide it by your expected or theoretical, and then sum it up for each of these categories, sum all those up, and what you're going to get is you're going to get a chi-square of 12.68. That's the number you're going to get. You could also take the z number and add all those up. Take the square of each of the z numbers, add them up, and it'll also end up being 12.68. So in any case, you take that chi-square, you look how many degrees of freedom do you have for this particular problem. Well, I hope that you said 4, because there's 5 categories, n minus 1, that's 5 minus 1, that's 4. So your degrees of freedom is 4. You're still working with a 0.05% distribution. So you're looking at 11.07, right, is your critical value. I'm sorry, 9.48 is your critical value. So as you see here, it shows you 9.48. And you'll note that 12.68 is bigger than 9.488. So you have to say that this distribution here is not due to randomness. It's not due to randomness. You are rejecting the null hypothesis. So at this point, you have to wonder, there's some kind of cheating going on. Is there a problem with the decks? But something's going on. This distribution is not due to randomness. All right, let's take a look at the next problem set. So, okay, this one's a genetic engineering problem, and you'll see here that in this problem set, this genetic engineer decided to cross a cheetah with a tiger to see if she can get a specific type of phenotype. And she predicted she would end up with four individuals, 4 zygotes that have stripes only, 3 that have spots only, 9 that have stripes and spots only. So that's what she's predicting. So that's the theoretical, or the expected results. All those words pretty much mean the same thing in this context. So when the cross was performed, she counted individuals. She found 50 stripes, 41 spots, and 85 with both. So the question is, when you do your chi-square, did her theoretical match her actual or observed? So your expected ratio, your expected ratios are 4 to 3 to 9. So 4 out of 16, 3 out of 16, 9 out of 16. Now that gives you a percentage, and you take that percentage and you multiply it by the total actual. And what you expect then is 44 with stripes, 33 with spots, and 99 with stripes/spots. So that would be your expected values. Your observed values are such, 50, 41, and 85. When you subtract your expected from the observed, these are the values you get. When you square it, this is what you get. When you divide it by the expected, these are your values. When you sum them up, this is your chi-square. So your chi-square value is here, 4.74. Now, when you take that 4.74 chi-square value, and you just start to decide how many degrees of freedom do you have? How many degrees of freedom do you have? You have how many categories you have? Well, I hope you said 3. You have 3 categories, 1, 2, and 3. Minus 1 is 2, so you're looking at the second degrees of freedom. You're looking at 0.05, and you see you get a 5.991, which is your critical value. So you see 4.74 is less than 5.991. So the discrepancy between the expected and the observed is due to randomness. You are accepting the null hypothesis. All right, let's move on. Okay, this answer set, the writer of this answer set decided to go ahead and use ratios and solve for x. So this individual solved for x for each of these. I said to you, you don't have to do that. What you could do is say 9 divided by 16. That gives you a certain percentage. So you get 9 divided by 16 gives you 56.25%. So if you take that 56.25% and multiply, or 0.5625, and multiply it by 994, that's going to give you a number. It's going to give you about 559. So this is your expected value you see here. So it's the same number, it's just 2 different ways of calculating, so don't get confused. I told you find out what percentage you expect to get. It's 9 out of 16. That gives you a percentage of 56.25. You multiply that times the total number of individuals you actually got, and this is what you'd expect to get out of this particular population. So if you see here that you'll note that you're taking 556 minus 559, because your expected is 559, you actually got 556, so this is observed, and this is expected, right? And you're dividing by 559 because that's your expected, all right? And so over and over again, you do it, and you're summing up each of these, this one plus this one plus this one plus this one, and you're getting a value, and that value is your chi-square. Okay, once you do that chi-square, you compare it to your chart, and you decide whether this is due to randomness, or is this difference between the expected and the actual, is that difference too big to be random? Is there something wrong with the theory, or is there something wrong with your assumptions? All right, so that's it for this problem set. Good luck.